Welcome back. I have charged the camcorder again. This is my 10 years old Canon. Yes, but it can still record text very clear. And I did cook some hot foods, rice with onions. I made a video about that. Let's get a little bit to drink, like lemonade juice. So I start to get tired because I did wake up like 10 times tonight. I was watching YouTube like late night, and then I should rest like 10 minutes, and then I did fall asleep. Then I wake up around midnight, and then I wake up like 1 a.m. Then I wake up many times through the night. Then early in the morning, I think, in the night I did close my computer and stop. But it's the 15th September today. They just start to put heating on. That's the first day with heating, but I'm not have heating on my radiators. I keep it on 0, but this metal pipes I cannot take off, of course. I have this metal pipes everywhere in my apartment, so it gives a little bit heating. So now it's like 25. That's because the sun has been shining a little bit. But let's continue. I did finish the Pentium M. That's the Pentium Mobile M. You have a Celeron M and stuff, but that's another kind of stuff. You can maybe read about that later, but let's just continue my list. Multi-core processors. Then we got the Pentium D and the Pentium Dual Core. I think we have a Pentium D or Pentium Dual Core here. I don't think it's a Pentium 4, because if it was a Pentium 4 it will say that. I think it's a Pentium Dual Core. No, this old cheap gamer computer I buy on the Danish Blue Papers, Danish second hands. You can get less $100. Some of them have the old Pentium D. Yes, I need a minute to adjust my my camcorder. Yes, then I need half a minute to go to my bed. But the old the Pentium and Pentium 1, 2, and 3 and 4, I think that was single core CPUs like the Intel 486 and 386. So now they start to make multi-core. And we have another, Intel have a brand called Intel Core. We will read about later. And they have a Pentium, no, they have a Intel Core 2 brains. Yes, but I start to get tired. Oh, I had to scratch my eye, so yes, but this would be 2-part videos.
Multi-core processor. Diagram of a generic dual-core reprocessor with CPU local level 1 caches and a shared, on-die level 2 cache. An Intel Core 2 Duo E6750 dual-core reprocessor. An AMD Athlon X26400 plus dual-core reprocessor. A multi-core processor is a microprocessor on a single integrated circuit with two or more separate processing units, called cores, each of which reads and executes program instructions. 1. The instructions are ordinary CPU instructions, such as add, move data, and branch, but the single processor can run instructions on separate cores at the same time, increasing overall speed for programs that support multi-threading or other parallel computing techniques. 2. Manufacturers typically integrate cores onto a single integrated circuit die, known as a chip multiprocessor or CMP, or onto multiple dies in a single chip package. The microprocessors currently used in almost all personal computers are multicore. A multicore processor implements multiprocessing in a single physical package. Designers may couple cores in a multicore device tightly or loosely. For example, cores may or may not share caches, and they may implement message passing or shared memory inter-core communication methods. Common network topologies used to interconnect cores include bus, ring, two-dimensional mesh, and crossbar. Homogeneous multi-core systems include only identical cores. Heterogeneous multi-core systems have cores that are not identical. E.G.Big.Little have heterogeneous cores that share the same instruction set, while AMD accelerated processing units have cores that do not share the same instruction set. Just as with single processor systems, cores in multi-core systems may implement architectures such as VLI, superscalar, vector, or multi-threading. Multi-core processors are widely used across many application domains, including general purpose, embedded, network, digital signal processing, DSP, and graphics, GPU. Core count goes up to even dozens, and for specialized chips over 10,000, and in supercomputers, i.e. clusters of chips, the count can go over 10 million, and in one case up to 20 million processing elements total in addition to host processors. 4. The improvement in performance gained by the use of a multi-core processor depends very much on the software algorithms used and their implementation. In particular, possible gains are limited by the fraction of the software that can run in parallel simultaneously on multiple cores. This effect is described by Bindoll's law. In the best case, so-called embarrassingly parallel problems may realize speed-up factors near the number of cores, or even more if the problem is split up enough to fit within each core's cache, avoiding use of much slower main system memory. Most applications, however, are not accelerated as much unless programmers invest effort in refactoring. 5. The parallelization of software is a significant ongoing topic of research. Co-integration of multiprocessor applications provides flexibility in network architecture design. Adaptability within parallel models is an additional feature of systems utilizing these protocols. 6. Contents. Terminology. Development commercial incentives. Technical factors. Advantages. Disadvantages. Hardware trends. Architecture. Software effects licensing. Embedded applications. Network processors. Digital signal processing. Heterogeneous systems. Hardware examples: commercial, free, academic. Benchmarks. See also. Notes. References. Further reading. External links. Terminology. The terms multi-core and dual-core most commonly refer to some sort of central processing unit, CPU. But is sometimes also applied to digital signal processors, DSP, and system on a chip, SoC. The terms are generally used only to refer to multi-core microprocessors that are manufactured on the same integrated circuit die. Separate microprocessor dies in the same package are generally referred to by another name such as multi-chip module. This article uses the terms multi-core and dual-core for CPUs manufactured on the same integrated circuit, unless otherwise noted. In contrast to multi-core systems, the term multi-CPU refers to multiple physically separate processing units, which often contain special circuitry to facilitate communication between each other. The terms many-core and massively multi-core are sometimes used to describe multi-core architectures with an especially high number of cores, tens to thousands. 7.8
Yes, sir. I got that text message just to reply. Have to read page by page because I have to reboot this program.
Some systems use many soft microprocessor cores placed on a single FPGA. Each core can be considered a semiconductor intellectual property core as well as a CPU core. Development. While manufacturing technology improves, reducing the size of individual gates, physical limits of semiconductor-based microelectronics have become a major design concern. These physical limitations can cause significant heat dissipation and data synchronization problems. Various other methods are used to improve CPU performance. Some instruction-level parallelism, ILP, methods such as superscalar pipelining are suitable for many applications, but are inefficient for others that contain difficult-to-predict code. Many applications are better suited to thread-level parallelism, TLP, methods, and multiplying dependent CPUs are commonly used to increase a system's overall TLP. A combination of increased available space, due to refined manufacturing processes, and the demand for increased TLP led to the development of multi-core CPUs. Commercial incentives. Several business motives drive the development of multi-core architectures. For decades, it was possible to improve performance of a CPU by shrinking the area of the integrated circuit, IC, which reduced the cost per device on the IC. Alternatively, for the same circuit area, more transistors could be used in the design, which increased functionality, especially for complex instruction set computing, CISC, architectures. Clock rates also increased by orders of magnitude in the decades of the late 20th century, from several megahertz in the 1980s to several gigahertz in the early 2000s. As the rate of clock speed improvements slowed, increased use of parallel computing in the form of multi-core processors has been pursued to improve overall processing performance. Multiple cores were used on the same CPU chip, which could then lead to better sales of CPU chips with 2 or more cores. For example, Intel has produced a 48-core processor for research in cloud computing. Each core has an x86 architecture. 9, 10. Technical factors. Since computer manufacturers have long implemented symmetric multiprocessing, SMP, designs using discrete CPUs, the issues regarding implementing multi-core processor architecture and supporting it with software are well known. Additionally, using a proven processing core design without architectural changes reduces design risk significantly. For general-purpose processors, much of the motivation for multi-core processors comes from greatly diminished gains in processor performance from increasing the operating frequency. This is due to 3 primary factors. Smiley 11. 1. The memory wall, the increasing gap between processor and memory speeds. This, in effect, pushes for cache sizes to be larger in order to mask the latency of memory. This helps only to the extent that memory bandwidth is not the bottleneck in performance. To the ILP wall, the increasing difficulty of finding enough parallelism in a single instruction stream to keep a high-performance single-core processor busy. Three, the power wall, the trend of consuming exponentially increasing power, and thus also generating exponentially increasing heat, with each factorial increase of operating frequency. This increase can be mitigated by shrinking the processor by using smaller traces for the same logic. The power wall poses manufacturing, system design and deployment problems that have not been justified in the face of the diminished gains in performance due to the memory wall and ILP wall. In order to continue delivering regular performance improvements for general-purpose processors, manufacturers such as Intel and AMD have turned to multi-core designs, sacrificing lower manufacturing costs for higher performance in some applications and systems. Multi-core architectures are being developed, but so are the alternatives. An especially strong contender for established markets is the further integration of peripheral functions into the chip. Advantages. The proximity of multiple CPU cores on the same die allows the cache coherency circuitry to operate at a much higher clock rate than what is possible if the signals have to travel off-chip. Combining equivalent CPUs on a single die significantly improves the performance of cache snoop, alternative, bus snooping, operations. Put simply, this means that signals between different CPUs travel shorter distances, and therefore those signals degrade less. These higher quality signals allow more data to be sent in a given time period, since individual signals can be shorter and do not need to be repeated as often. Assuming that the die can physically fit into the package, multi-core CPU designs require much less printed circuit board (PCB) space than do multi-chip SMP designs. Also, a dual-core processor uses slightly less power than two coupled single-core processors, principally because of the decreased power required to drive signals external to the chip. Furthermore, the cores share some circuitry, like the L2 cache and the interface to the front-side bus, FSB. In terms of competing technologies for the available silicon die area, multi-core design can make use of proven CPU core library designs and produce a product with lower risk of design error than devising a new wider core design. Also, adding more cache suffers from diminishing returns. Multi-core chips also allow higher performance at lower energy. This can be a big factor in mobile devices that operate on batteries. Since each core in a multi-core CPU is generally more energy efficient, the chip becomes more efficient than having a single large monolithic core. This allows higher performance with less energy. A challenge in this, however, is the additional overhead of writing parallel code. 12. Disadvantages. Maximizing the usage of the computing resources provided by multi-core processors requires adjustments both to the operating system, OS, support and to existing application software. Also, the ability of multi-core processors to increase application performance depends on the use of multiple threads within applications. Integration of a multi-core chip can lower the chip production yields. They are also more difficult to manage thermally than lower density single-core designs. Intel has partially countered this first problem by creating its quad-core designs by combining two dual-core ones on a single die with a unified cache. Hence any two working dual-core dies can be used, as opposed to producing 4 cores on a single die and requiring all 4 to work to produce a quad-core CPU. From an architectural point of view, ultimately single CPU designs may make better use of the silicon surface area than multiprocessing cores, so a development commitment to this architecture may carry the risk of obsolescence. Finally, raw processing power is not the only constraint on system performance. Two processing cores sharing the same system bus and memory bandwidth limits the real-world performance advantage. In a 2009 report, Dr. Johnny showed if a single core is close to being memory bandwidth limited, then going to dual core might give 30% to 70% improvement. If memory bandwidth is not a problem, then a 90% improvement can be expected. However, Amdahl's law makes this claim dubious. 13. It would be possible for an application that used TWIPAS to end up running faster on a single core one if communication between the CPUs was the limiting factor, which would count as more than 100%. Improvement. Hardware trends. The trend in processor development has been towards an ever-increasing number of cores, as processors with hundreds or even thousands of cores become theoretically possible. 14. In addition, multi-core chips mixed with simultaneous multi-threading, memory on chip, and special-purpose heterogeneous, or asymmetric, cores promise further performance and efficiency gains, especially in processing multimedia recognition and networking applications. For example, a big. Little core includes a high-performance core, called big, and a low-power core, called little. There is also a trend towards improving energy efficiency by focusing on performance per watt with advanced fine-grain or ultra-fine-grain power management and dynamic voltage and frequency scaling, i.e. laptop computers and portable media players. Chips designed from the outset for a large number of cores, rather than having evolved from single-core designs, are sometimes referred to as many-core designs, emphasizing qualitative differences. Architecture. The composition and balance of the cores in multi-core architecture show great variety. Some architectures use one-core design repeated consistently, homogeneous, while others use a mixture of different cores each optimized for a different, heterogeneous role. How multiple cores are implemented and integrated significantly affects both the developer's programming skills and the consumer's expectations of apps and interactivity versus the device. 15. A device advertised as being octa-core will only have independent cores if advertised as true octa-core, or similar styling, as opposed to being merely two sets of quad cores each with fixed clock speeds. 16. 17. The article CPU Designers Debate Multi-Core Future by Rick Merritt, E. Times 2008, 18, includes the comments Chuck Moore suggested computers should be like cell phones, using a variety of specialty cores to run modular software scheduled by a high-level applications programming interface. Atsushi Hayasakura, a senior chief engineer at Renesas, generally agreed. He suggested the cell phone's use of many specialty cores working in concert is a good model for future multi-core designs. Anant Agarwal, founder and chief executive of startup Tylera, took the opposing view. His 8 multi-core chips need to be homogeneous collections of general-purpose cores to keep the software model simple. Software effects. An outdated version of an antivirus application may create a new thread for a scan process, while its GUI thread waits for commands from the user, for example cancel the scan. In such cases, a multi-core architecture is of little benefit for the application itself due to the single thread doing all the heavy lifting and the inability to balance the work evenly across multiple cores. Programming truly multi-threaded code often requires complex coordination of threads and can easily introduce subtle and difficult-to-find bugs due to the interweaving of processing on data shared between threads. See thread safety. Consequently, such code is much more difficult to debug than single-threaded code when it breaks. There has been a perceived lack of motivation for writing consumer-level threaded applications because of the relative rarity of consumer-level demand for maximum use of computer hardware. Also, serial tasks like decoding the entropy encoding algorithms used in video codecs are impossible to parallelize because each result generated is used to help create the next result of the entropy decoding algorithm. Given the increasing emphasis on multi-core chip design, stemming from the grave thermal and power consumption problems posed by any further significant increase in processor clock speeds, the extent TOHIC software can be